is a map from, yep, it's all right. So it followed the water. This is a map from a number of years ago now, or last year, I suppose, of all of the lakes that have been identified on Mars. In the red and blue circles. So red is closed basin lakes, ones which were likely not fed by rivers or have outflowing rivers, and then open basin lakes for ones which have outflowing locations. And then there's these thermokarst lakes having to do with melting processes there as well. And what you can see right away is that there's a lot of lakes on Mars, right? We have identified many lakes and many potentially habitable environments on Earth. And we've actually sent rovers to some of these lakes. So here is Spirit. Spirit was one of the Mars exploration rovers that was sent there early in this millennium. We also have Curiosity, which is the rover that I'm going to talk about and the team that I'm on. And then finally, Perseverance, which is in Jezero Crater and landed a couple of years ago now, and has been exploring Jezero Crater and drilling samples to bring back to Earth. So for many reasons, not the least of which is that I'm on the team, Curiosity is the coolest of these three rovers. So Curiosity, importantly, I might have lost the ability to change the slide. There we go. Great. So here's Curiosity in its clean room laboratory at the Jet Propulsion Laboratory at Caltech, or near Caltech in California. And you can see Curiosity is a giant rover. Okay? It's much larger than Spirit. Perseverance is essentially the same size as Curiosity. It's got essentially the same chassis. Got different instruments on board, but it was designed effectively to have a laboratory internal to it that is able to explore the planet quantitatively for signs of habitability. Advance, please. So here are the instruments all labeled on Curiosity. So the ones that as a geochemist, that I'll focus on the most are this one here, ChemCam LIBS. And so it has a laser that's able to shoot rocks up to 10 meters away and get the chemical composition of those rocks through a laser plasma emission process. The one internal to the rover, ChemIn, which is the mineralogy instrument. So if you've ever heard of an X-ray diffraction or X-ray diffractometer, that's what ChemIn does. SAM, I won't talk about very much, but SAM is an incredible tool. It's actually a mass spectrometer that's on another planet. So we can do things like oxygen and sulfur and hydrogen isotopes on Mars, which is really, and carbon isotopes on Mars. And then one of the things that facilitates basically everything that we do is this drill. And so the Curiosity rover has a drill that's able to drill up to 30 or 40 millimeters into the subsurface, and then it can scoop up those samples, drop them into the rover, as I'll show in a couple of slides here, to analyze their chemistry and mineralogy quantitatively. And then, of course, the most important thing, or one of the most important things, is its ability to take very good pictures all the time. And so Mastcam is very good for that as well. So how does the team work? How do we actually operate and command the rover to do the science that we want to do? So night on Mars, we get what is called a downlink. So it uses the deep space network to send data back to us here on Earth. So there we all wake up in the morning with a nice fresh quantity of data to analyze for the next day. And also for the 2 to 4 days before then, we've been planning a new set of commands to send to Mars. So we send that back through uplink. In daytime on Mars, Curiosity starts doing the things that we ask it to do, like drive this far, analyze these rocks, take these pictures, and so on. That's while we're sleeping. We then get the data back and begin to analyze it and begin to make decisions about what we do next. So this is one of the things that I sort of didn't really realize whenever I joined the team, is that you're always on, right? You're always getting new emails, new data to look at and try and analyze, make decisions about where the rover should be going next. So this process takes about 15 minutes of sending information between Earth and Mars. So one set of instructions a day, basically, ideally at the end of the day on Earth, and the beginning of the day on Mars. It's being sent. And this is essentially what that looks like. So we uplink the data, Curiosity does something for us, or uplink the commands, Curiosity does something for us, it downlinks it to us. We then process that data using algorithms and processing scripts here on Earth. We assess it to see, well, is it interesting? Do we need to do it again? Is it something that we should explore further, and so on? We plan that, we generate a sequence, and this is really there's a lot of horse trading involved in this. So people might want to do geochemistry, other folks might want to observe wind patterns or something like that. So there's only so much science you can do in a day. And basically everyone needs to compete over that amount of time. And then ultimately it's validated. For sure, we're going to have enough battery life to do this today. For sure, we're going to be able to do these amounts of analyses in this amount of time. And then we send it up to Mars to go. So one of the important things about Curiosity, you can see it here, and is sort of one of the largest constraints on its ability to do analyses is that it is run by a radionuclear generator, which charges a battery, and the battery discharges as we use it for science during the day. And so basically everything is limited by the amount of battery life we can get on a single day. Oops. All right, so what we've been doing and why this was chosen as the place to go in Gale Crater on Mars is that this Mount Sharp in the center of the crater is approximately 5 kilometers of continuous sediment from the bottom of the crater up to the top of the crater. And so very few places on Earth will have such a beautiful continuous record of sedimentology through such a large interval of space. And so we started exploring down here in the Murray Formation, hematite bearing unit, or so-called Vera Rubin Ridge, and then clay bearing unit, and I'll mention something about the clays. And then finally, where we are now is up in this magnesium sulfate unit. So many years ago, probably about 15 or 20 years ago, whenever the original idea of sending Curiosity to Mount Sharp was conceived, and Gale Crater was conceived, the idea was someday we're going to be able to get to this magnesium sulfate bearing unit and ultimately see the transition between the clays and the magnesium sulfates that I'll talk about today. So between wet conditions and dry conditions. So this is an image of Curiosity's heat shield as it actually landed. So it launched in November 2011, so 12 years ago now, and it finally reached Mars in August 2012. And this is it as it sort of landed or lowered itself to the planet. And then this is the touchdown, August 5th, 2012. Touchdown confirmed, time to see where our Curiosity will take us. And there's been many accomplishments in that time. And again, we've been climbing this Mount Sharp in the center of the crater that whole time. So Curiosity's goal, its mission, was to find a habitable environment on Mars. And it finished that task, that mission, right after landing. First analysis, right? So this shows that. This is a conglomerate rock from the base of the crater. And it looks a lot, probably familiar to many of us, right? Even if you're standing in parts of the Bell River, you'll see rocks that look like this today. It's clearly stones that have been transported by a river and ultimately been cemented by aqueous processes in the base of the crater. And interestingly, there's also near that area where the conglomerates were observed, there's these lowest levels of Mount Sharp that actually consist of this very fine-grained laminations, ultimately looking like a sedimentary rock that we would probably see on Earth, something that we might call a mudstone here on Earth. And they likely formed from mud in an ancient lake. So the model for at least that deep part of Gale Crater is this, right? So we have rivers flowing into a very deep crater, making lake deposits at the bottom of the lake. So we end up getting some of these delta deposits that are those conglomerates, and then we also see the thinly laminated sediments at the bottom as well. And so this is the summary of that initial discovery of the first year that Curiosity was on Mars. Ultimately, there's an ancient river system that was flowing into this crater. It was intermittently wet lake bed, so it wasn't always full to the brim, but it also ultimately had a lake there. There was sustained interactions with water that allowed us to, and the mineralogy of what we see there, it shows that it's not too acidic or alkaline, so it's actually fairly neutral in its conditions, low salinity, and therefore the conditions were ultimately not strongly oxidizing. All of this to indicate that the key chemical ingredients for life are present. So schnapps, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are all there. And then ultimately, we know because there's iron in different oxidation states, manganese in different oxidation states, that a primordial life form could have made a living off of the different oxidation states of materials that are there. And so this is an artist's depiction of the very habitable ancient Gale crater lake on Mars. Remember, this Mount Sharp in the center of the crater is 5 kilometers high, right? So this is a very, very deep lake that was there on Mars. And I like to think, if you look at this, oops, and you could just imagine putting a nice little lawn chair there and then hanging out at the beach there on Mars. It's actually that kind of habitable environment. So early Mars looked a lot like Earth today. Of course, you'd have to have some sort of oxygen mask with your swimsuit in order to swim in the lake, but that's a minor detail. Okay, so we know we had, within a year of Curiosity being on Mars, strong evidence that there was liquid water, that there were lakes there on the ancient planet. But if we run a climate model of ancient Mars and use the same types of gases we have here on Earth to heat the atmosphere, so major greenhouse gas being carbon dioxide, ultimately you cannot get the planet warm enough. And so this is showing the evidence that we have ancient lakes on Mars or water on the ancient Martian surface. So valley networks, crater degradation. So ultimately the rims of the crater are being caved in by flowing water. And then phyllosilicates, that's clay minerals, sulfates and evaporates that indicate water drying up, manganese oxides mediated by water moving on the planet. So we have strong evidence from 3 billion years ago and earlier that there was liquid water on the planet. But today, obviously, we have none of that. And so this is a plot of the amount of time the planet was above freezing in its early history based on a model of the early Martian atmosphere. And I know it's fairly detailed, but the important thing to point out is that the time of warmness or above zero in millions of years, and this is a histogram, seems to have been no more than several millions of years in the entire history of the planet. So it was habitable, but it wasn't habitable for very long, effectively, because it was very cold and it's hard to heat. And the way that folks think that you had to get the ancient planet warm, or what you had to do to the atmosphere, or the atmosphere had to have in it be warm, is hydrogen gas. So unlike Earth, we might have had a small amount of hydrogen gas in our early planet, but we largely believe that it was carbon dioxide that was able to heat the planet. On Mars, it seems that carbon dioxide can't do it. You need something else, you need hydrogen. And so we need to look at the processes that might have produced hydrogen on ancient Mars. So a warm, wet, early Mars apparently needed hydrogen in order to trap heat. And the question is, how do planets make hydrogen? Serpentinization is a key reaction in this. And this happens not just on Earth, not just on Mars, but there was a paper earlier this week about serpentinization reactions happening on moons like Enceladus. The serpentinization is sort of a ubiquitous process that I'm going to walk you through now that could have made hydrogen on early Mars as well. So it's a very common planetary process. What it does is adds water to olivine, oxidizes iron, and produces hydrogen. So this is a rock that we call dunite. If you've ever heard of the gemstone for the month of August, peridote, that's it. It's olivine or peridote that makes up this rock. And so this is actually what the Earth's upper mantle is made out of. So if you go down below the crust and you look at the rocks that are there, it's this stuff. It's green, beautiful olivine. If you add to that water, and this is a very specific amount of water for a very specific reason, but if you add to a kilogram of rock, 1,302 milliliters of water, you end up with this rock here. And this is an exhibit from the Smithsonian Museum in Washington, D.C. And you make this rock called a serpentinite. So this rock is a rock. It doesn't feel wet, but it started with no water in it at all as a peridotite and became a serpentinite, this rock on the right-hand side, through the addition of water and the production of minerals like serpentine. And so this rock, this kilogram-sized rock here has 12.5% water in it. And that process of adding water to this iron-rich rock ultimately makes hydrogen gas. Okay, so this is just a plot of a whole bunch of chemical analyses, and I know that I'm a geochemist and I love these things, but many people don't. So I will walk you through slowly what actually is being shown here. So as we go from the left side to the right-hand side, we're going with increasing amounts of this chemical reaction. We're making more and more serpentine, more and more hydrogen. And then this y-axis here is iron oxidation. So as we go from iron 2+, so iron that's ultimately in that original green olivine, is being oxidized, and it's becoming iron 3+, and it's ultimately becoming or producing hydrogen during that process. So this is what one of those rocks looks like under the microscope. It's quite beautiful. This stuff is olivine, that same green mineral that we saw before. But when you cut it very thinly and look at it under a polarizing microscope, you ultimately see these beautiful colors as a result of its patterns in the microscope. And then we're making in the process this serpentinite rock here, where you see minerals like magnetite, that black stuff that's in the middle of the veins, and then other minerals like serpentine, which is crisscrossing the olivine there. And so we can easily go and calculate from the amount of iron that's in the rock and the amount that became iron 3+ or oxidized iron, the amount of hydrogen that's being produced. And so we can actually, just by analyzing a rock, know how much serpentinite rock, know how much hydrogen was produced during the water-driven alteration of that rock. And so it's important to know that Mars is actually a very different planet than Earth for many reasons. But one of the most important ones is that Mars is red, right? Mars is red because it has a lot more iron. Not all olivines are created equal. So this is an example of olivines from our Earth's mantle, the rocks from our Earth's mantle. On the right-hand side is a palisite. I'm sure if you've been to any of the mineral shops in Banff or elsewhere, you've probably seen something like this before. Ultimately, this is thought to be a core of an ancient planetesimal. And that stuff in there, the bright yellowish green stuff, is the same mineral olivine, but it's got a different iron concentration than the stuff that we get in our mantle. So ultimately, because we can do that calculation, here's how much oxidized iron we have, here's how much hydrogen we have. You can do the same thing if you have a different amount of iron as well. Okay, so olivines of Earth's mantle contain very little iron, actually. So here's an olivine fraction of iron, so a fraction of 1 up here and a fraction of 0 down here in the olivine. And we're going between the minerals forsterite down here, so magnesium olivine, and phthalite up there. So there's forsterite. It's got the chemical formula where it's just magnesium and silicon and oxygen. And then this guy up here is phthalite, iron, silicon, and oxygen. And what you can see right away is that that beautiful green mineral from Earth's mantle is nearly all magnesium olivine or forsterite. But the question is, how do Martian olivines compare to terrestrial mantle olivines? We already know, right, that Mars is the red planet for a reason. It's got a lot of iron in it. But how much more iron do those olivines have? Fortunately for us, Curiosity has analyzed olivines in situ on Mars. So this is a video of Curiosity's Chemin instrument. So it has this hopper where we can put the sample once we've drilled it and drop it into the belly of the rover. And then once it's in there, this works. One more. There we go. Thank you. So this is a window that's made out of kapton or another material that's chemically inert, and we are firing an X-ray beam generated by the rover through that material as it's being sonicated, so shaken up and randomized, and then collecting the diffracted X-rays on a detector on the opposite side of the sample there. And so we have the sample and we're producing a pattern of rings here, which are representative of the minerals in the sample. And so as we do this, and we can do it for a number of analyses over a number of nights, we can end up getting quantitative mineralogy of the materials that we've drilled. And so there's only ever been 4 that have been analyzed by Curiosity on Mars, and there they are. You can see right away they've got a lot more iron in them than the Earth's mantle. We then go and get all of the meteorites that we believe to have delivered from Mars to Earth and analyze their olivines. We have 2 populations, one that looks very much like those ones that we see in Gale Crater, and then another population that's much more iron-rich, or sorry, much more olivine poor, but iron-rich olivines, which are probably not representative of serpentinization reactions. So right away, we can see that every olivine that's ever been analyzed on Mars contains much, much more iron than any olivine that's in Earth's mantle. So if we want to understand the hydrogen greenhouse and the ability of early Mars to warm itself, we need to understand how these specific olivines generate hydrogen during serpentinization. And so we have to go and look for weird serpentinites here on Earth in order to understand normal serpentinites on Mars. And a good place to go and look for that is a place that happens to be very close to where I did my PhD, the Duluth complex in northern Minnesota, right along the north shore of Lake Superior, sort of a bit south of Thunder Bay. And if we go and look at those, you can see that they actually line up perfectly with the olivines that have been analyzed in these olivine-rich rocks from meteorites, and then also all of the ones that we've analyzed in Gale Crater as well. And so here's the Duluth complex. The Lake Superior is down here. Of course, there's Minnesota. And the yellow part here are these olivine-rich rocks. So it's quite an extensive unit. We can actually just drive and camp down here near Duluth and get some really nice samples like this one on the right-hand side here. And so you can see right away that there's this brown stuff in between all of these grains of clear olivine. And that brown stuff is serpentine. So iron-rich serpentine. And then the black stuff is magnetite. Iron-rich magnetite also produces hydrogen during serpentinization. Okay, so here's those plots I showed before where we have oxidized iron on the y-axis, water on the x-axis in both cases, and importantly, the amount of hydrogen we generate there on the right-hand side. If we then go and look at the ones from the Duluth complex, so here's the oxidized iron over total iron in sample of Duluth complex, and in the background there are those samples from a compilation of Earth-based serpentinites. You can see that the more things change in terms of iron composition, the more they actually stay the same. Basically, the trend in terms of ratio of oxidized iron with total iron versus water addition is identical. But if you go and then plot the total amount of iron that's been oxidized on the y-axis, as well as the moles of hydrogen being produced, you see right away that serpentinites on Mars produce a heck of a lot more hydrogen than serpentinites on Earth. About 5 times more than serpentinites on Earth. So hydrogen is being produced as these interesting minerals, magnetite and iron-rich serpentine or hissengerite grow. So even if Mars is only weakly serpentinized, so even if there's not actually that much serpentine on Mars, serpentinization likely played a significant role in its biogeochemical evolution. So this is a orbital spectroscopy map of identifications of serpentine minerals on Mars. And right away, you can see that the places that they've looked in the black circles here all suggested originally that there's no serpentine. The squares are serpentine probably there, and then the stars are definitely that there's serpentine there. But the interesting thing about this study is that they were looking for a different kind of serpentine than the one we see in the Duluth complex. They're looking for chrysotile or lizardite, basically asbestos. And what we found in the Duluth complex is a very different mineral called hissengerite. We then repeat that analysis for minerals like hissengerite, that's all of these circles here. We see that actually there's probably serpentine all over Mars. And so actually serpentinization reactions likely produced significant amounts of hydrogen early in the planet's history. And that's how the planet became warm. And the really cool thing about serpentinization as a solution to this problem is that serpentinization also, or hydrogen also escapes from the planet, and that is a mechanism for cooling it as well. Interestingly, and this is just a quick aside, those mass spectrometers on the Curiosity rover instrument have also found organic molecules of the type that might be produced during serpentinization reactions. So one of the dominant hypotheses for the origin of life here on Earth is known as the alkaline vent hypothesis, or the idea that these serpentinization reactions produce the first life forms on our planet. And interestingly, we see these organic molecules that may or may not have been formed through serpentinization reactions that would be consistent again with this overall theory for how hydrogen came to warm the early planet. Well, ultimately what happened though is that hydrogen waned. So it warmed the planet, but then because Mars has no magnetic field and it has a much lower gravity than our planet, it's about third the size, the solar wind is just continually blowing that hydrogen off into space. So you can't make it essentially fast enough to maintain a significant greenhouse for over long geological timescales. Right. So habitability, again, coming back to this, I had a really nice figure, but I guess I lost it. showing that we've actually observed this on Earth. We've shined spectrometers back at Earth, and we've seen the hydrogen on Earth escaping out into space. So we know that this happens. Hydrogen is a very slippery molecule that sneaks off into space quite easily. Okay, so again, now we have evidence for how early Mars warmed itself, or how it became warm and habitable, but ultimately what happened to make this red, cold planet that we see today? How did these things change in order to end up with where we are today? And so we have evidence increasingly of a drier or drying Mars. And so these are mud cracks on Mars. This place is called Old Soker. And you can see that there's mineralized mud cracks, a lot like you might see at the edge of a dry lake today on Earth. So this is a clear evidence that there were places on Mars, or periods of time on Mars, where it was increasingly dry and there was no water in the Gale Crater Lake. And so, as I mentioned earlier, so as of mid-2022, but ultimately by now we've traveled significantly further. Curiosity has driven over 18 miles and climbed over 2,100 feet in elevation. So I just looked at the number from earlier this week. It's about 30.8 kilometers is how far Curiosity has driven. So not particularly far. Probably some of you actually drove further than that to come here tonight, but it's slow going. So 5 meters a day usually, something like that. And we're currently, again, exploring, and we've come up to this place on Mount Sharp where we're at this magnesium sulfate bearing unit. Where we're looking at this record of drying there on the planet. Okay, so to contextualize the things that I'm about to say, it is important to start to think about how salty things that we actually know are. Does anyone know which of these numbers is the saltiness of the ocean? Like how much of the ocean is actually salt versus how much of it is water? Less than 1%, 3.5%, or 35%? Anyone actually have any idea? 3? Yeah, it's 3.5% salt. The rest of it's water. And so even though the sort of the saltiest substance many of us will ever think of, unless we're oil and gas geologists that work on reservoir brines, most of it's still just water. And it's only about 3.5% salt. Interestingly, to make the magnesium sulfate minerals that we see on Mars, we've got to be a heck of a lot saltier than seawater, 5 times or more saltier than seawater. So getting up towards the 35% salt here. And so we have spectroscopic mapping of Gale Crater. So there's the clay bearing unit that we've explored for quite some time. And now we're in the sulfate bearing unit now. And in order to supersaturate this mineral magnesium sulfate, and it's very familiar to us, it's Epsom salt, you need to be on the order of 2 molar of magnesium and 2 molar of sulfate, or on the order of 15 or 20% salt on Mars, or in the waters on Mars. So the way that we are telling this, or the way that we were originally telling it, we've advanced somewhat in this, but most of that data is still under embargo. We are using this ChemCam LIBS instrument to zap materials using the laser-induced breakdown spectroscopy. So it's able to take very nice telescopic images. Then it has a laser that it can shoot off into the rocks around it, and then we can analyze the plasma that's produced as we evaporate those minerals, and we can analyze their chemistry to see exactly what they're made of. And here is an example of what those materials are made of. So we started in this Murray formation down here, the gray stuff, and then as we've moved upwards in the crater, we start to see more materials that, again, that we might be familiar with: calcium sulfate, gypsum, basanite, and anhydrite, other calcium sulfate materials. And we start to see magnesium sulfates, like this magnesium sulfate material, 21 weight % water, is something like epsomite, kieserite, and so on. So we're starting to see Epsom salt being present there on the planet. And that means that we are in a place where you're so dry that you're evaporating and precipitating almost everything that is in solution. And so here's where we're at. So this is, we're a bit onwards from this at this point. So 36 drill holes and counting. And so ultimately we have now 38. 2 of the most recent ones are still under embargo, but you can see just as we've gone through the crater, we've come across lots of interesting different materials. And one of the things that's most fascinating to me is when you look at this, like that even though the surface of the planet is often red, as soon as we drill underneath, we get gray, right? So that's really only a thin veneer of that super oxidized iron. And so the important thing that we're noticing using these X-ray diffractometer on Mars is that we went from very clay-rich rocks where we're seeing materials like nontronite and smectites to rocks that have no clays in them, and they have a lot of this magnesium sulfate material. So clay minerals, biosilicates, and an increase in sulfates as we go up, and we've actually now quantitatively identified magnesium sulfate minerals using the X-ray diffraction instrument. Oops. And so this is a little under a year ago at this point, where it was such an important time in the history of the mission that they had a press release that we finally have reached this long-awaited salty region. So again, it was a dream of the original proposers of this instrument 15 or 20 years ago to actually finally one day make it to analyze these rocks on Mars, the sulfate-rich rocks on Mars. And we finally made it there now, and it's certainly for me, as somebody that's just joined the team last year, is probably one of the most exciting things that I've ever been a part of. And so this is what it looks like. So we've gone from this clay bearing unit down here to this magnesium sulfate bearing unit where we're at now. So we're ultimately exploring what are those magnesium sulfates? What do they mean for the ancient habitability of the planet? And so again, going back to this hydrogen greenhouse effect, ultimately you see that these blue lines are going away over time, and that is contributing to this global drying. So it transitioned about 3.5 billion years ago from a hydrogen-rich atmosphere that was able to warm the planet to one where there was maybe a little bit of hydrogen, but no more liquid water capable of existing there. And again, these magnesium sulfates imply strongly evaporative conditions on the planet. So we have calcium sulfate, magnesium sulfate precipitating, and we end up seeing probably not really that big, beautiful lake that you can set your lawn chair up next to, but probably a lot of little brine pools that are existing there. Probably still habitable, probably still have the right ingredients for life, but not quite the dramatic lake that we saw before. And we're exploring that now. So this is taken on Sol 23, the 23rd Martian day that Curiosity was there, and that's where Curiosity is today. So again, I mentioned we've gone about 30 kilometers. That's about 30 kilometers as far as we can go, or as far as we've gone so far. And this is a postcard that Curiosity just sent back to us from Mars. They ultimately took 2 photos, one in daytime, one in nighttime, to make this beautiful transition. And they again released this quite recently to show that Curiosity is still alive and well on the planet, not particularly dusty. It's actually doing really well. And as we try to understand these magnesium sulfate brine pools that were likely existing on Mars, we have to start to try and understand places on Earth that looked like that. And we are very lucky here in Calgary to be very close to this place on the right-hand side, which is near Cache Creek, British Columbia. And it's a lake, quote unquote lake, that has a bunch of brine pools in it that are actually actively making magnesium sulfate or epsomite. That's what that white material around the pool is. And so the big struggle now is that we have evidence that we have these brine pools. And so ultimately evaporative conditions are required to originate life. We need this ability to concentrate the ingredients to make the first biomolecules. But ultimately, what if the water is too salty? If we did originate life, it might not be able to live there. Whoops. And so this is just a news release from a couple of days ago now. NASA's Curiosity Mars rover gets a major software upgrade. So even 10.5 years on, it still is innovating. The folks at JPL are still putting new and innovative software updates onto the rover. One of the things that it can do very well now is if we haven't given it a command, or if it's done something like it's wheel slipped or something like that, it is able to take pictures and analyses for us without us telling it, right? So it has the ability now a little bit to think for itself. And that's very powerful because that means there's no wasted days in terms of data analysis. So again, this is a large team effort. There's many different teams, many different instruments on Curiosity. And I can only just say that teamwork makes the dream work. So although I presented some interesting science today, I'm part of a much larger team who does much more of the work together. And so I want to say thanks for having me. And again, I'm happy to answer questions. Just show you this cool GIF here of a dust devil moving across Mars. That's picking up dust and moving there as well. So thank you very much.
Perfect. Thank you so very much for a wonderful presentation this evening. And as we move on to the Q&A period, I'd just like to remind those of you who are joining by Zoom, you can join into the question period by typing your question into the Q&A function on Zoom, and we will ask them live here at the Calgary Public Library Central Branch to Dr. Tutolo. And for those of you joining here in person, just raise your hand and we will get to your question. So while we get the other microphones setting up, I'd just like to ask a question that is online. Other than serpentinization, are there any possible processes to make hydrogen in the early Martian atmosphere?
Yeah, it's a great question. So the other dominant process that makes hydrogen even on Earth today is volcanic eruptions. Unfortunately, it's fairly minor. And so there's probably a constant background flux over, if you average over a long enough time scale, of hydrogen entering the atmosphere from volcanic emissions. But the cool or interesting thing about serpentinization is it has this positive feedback where if you add the water, you start the reaction going, you have more water, the reaction goes faster, you warm it up and so on. I think that's why many of us have latched on to serpentinization as a potential hydrogen source.
Hi, thanks for the great talk. I just got a couple of issues here. First of all, hydrogen's pretty light and it rises up pretty quick, and Mars is about half the size of the Earth, which implies, less gravity. There's that issue, but I didn't quite get the relationship between sodium chloride, a high concentration of salt, and the relationship to magnesium sulfate.
Right.
Basically.
Yeah, those are excellent questions. So hydrogen is a very slippery gas, and I had a really nice, I put it in here because I thought it was cool for this audience, but I think I uploaded the wrong version in the end. Of hydrogen slips out of our atmosphere constantly. We've had spectrometers looking at our planet and there's just hydrogen leaking off. And actually, it's believed that that's part of why Mars has that red veneer today, because ultimately you're generating a little bit of oxygen because the hydrogen is leaking out faster than the oxygen from water molecules in the atmosphere. So you have O2 being left behind and that oxidizes iron. So it's true, it does leak quickly. The thing is there's a maximum escape rate that we know that takes into account gravity and magnetic field and all these other things. So what we do in the paper that we talked about serpentinization is take that maximum escape rate and say, how fast do you have to run a serpentinization reaction to overcome it to actually begin to accumulate hydrogen in the atmosphere? And it's not at all unrealistic. It's actually quite easy to do. You just couldn't do it for 3 billion years. You'd have to do it for 1 million years at a time or something like that. And so that's the concept there. And then the relationship between magnesium sulfate and sodium chloride is very important and interesting. So interestingly, we rarely, if ever, find sodium chloride on Mars. So halite is almost never there. And that's an interesting thing if you think about it, because Mars is ultimately largely composed of basalt. There's fairly little sodium in basalt, especially Martian basalt, compared to basalt here on our planet. And ultimately, our oceans have evolved to have quite a significant amount of sodium chloride in them. Lakes on Mars seem to have had quite a significant amount of magnesium, calcium, sulfur in them, not so much sodium and chloride. So although I use the saltiness of seawater as a comparison, they're actually two completely different species. Yeah.
Great, thank you. I'll take another one online here. Have you ever visited the Mars yard at JPL? If so, what was your favorite part there?
I was supposed to go in October last year, but there was science to be done and I had to go do the science instead. It was, I think I will get to go very soon because we're allowed to go whenever we're visiting Caltech, but I didn't get to go last year.
Great talk, thank you. As Curiosity climbs Mount Sharp, is it climbing up to younger and younger sediments, and is there any estimate of what those ages are, or are they all more or less the same age? What's the timeline that it's moving through?
That's the $1 billion question, right? is the sediments are definitely younger, right? There's no question that we're going into younger and younger sediments. We're watching the planet evolve, but we really don't have a good idea for how fast Gale sedimented, right? So timescales that are feasible go from 100,000 years to 100 million years, right? So like that's basically the entire history of the crater, right? And so we used to be able to date materials like jarosite on Mars and get actual ages on Mars, but we can't do that anymore because the way the spectrometer is configured. So we only have a vaguely good idea of how the crater is itself, and then we can do things like count the amount of craters that have hit certain strata on the planet to get an idea of the age of surfaces. But ultimately, the whole crater was filled, and now it's not filled anymore. So even if we're counting the age of the surface, it's been scooped out. So we're looking at the age since it was scooped out. Yeah, it's a huge challenge.
Great, thank you. Another one from online. Can you tell us what is the highest brine concentration found on Earth in which living organisms have been found?
Yeah, it's probably somewhere like the Basque Lakes, the magnesium sulfate lakes in British Columbia. And again, those are on the order of 2 molar magnesium sulfate. And because magnesium and sulfate are both divalent ions, it's actually on the order of 4 molar ionic strength, which is incredibly salty. And there has been a longstanding discussion about whether actually in a lake like that, the organisms that are living could have possibly been in any way representative of the first organisms on a planet. So essentially everything that lives in the Basque Lakes or any magnesium sulfate lakes on the planet evolved to adapt to those conditions. They didn't start there. So they used to live somewhere fresher and they became okay with the saltiness. The question is whether you could ever start something in such a salty environment.
What about subsurface water on Mars? Because life on Earth is probably started as a chemoautotrophic.
Yeah.
And it doesn't really care about things like sunlight. It just wants a certain a temperature where liquid water can exist and minerals.
Yeah, I totally agree. I love it. And I think very optimistically, we can all think that perhaps there's organisms living in the subsurface of Mars today. There's no reason to, like, if it did evolve, if it's anything like life here on Earth, it could easily adapt to conditions that became harder. The question is whether you could start life in those environments, and it's not quite clear whether you can. But I agree. And there's a colleague of ours at the University of Toronto, Barb Sherwood-Weller, thinks about that a lot.
Great. Here's another question from online. How are the rover's wheels holding up? Will they last a few more years?
Good question. A lot of bad stuff happened really early on, and nothing has happened since. So the wheels look just the same way they did 5 years ago. Yeah, I don't know if I had a picture of it. I think the last one that I showed, the postcard, you might have gotten an image of what the wheels look like these days. Sorry, I don't think it can actually go back to show that. Oh, but yeah, the wheels have holes in them. Simply put, lots of holes in them. But the engineers have gotten a lot better at planning so that we don't destroy the wheels any further. So nobody is in any way worried about the wheels today. Yeah.
I know you're a geochemist and not a geologist. Your setup slide comment about the launch here. That image always bothers me. Mount Sharp is full of horizontal layers, clearly deposited in a lake. Is there any proof that there's a second lake that happened after that? That's essentially
Right.
I find that very unbelievable from the geological.
Yeah, I like to show that, like, for a couple of reasons. One thing I can say that's really interesting in that same context is that there's sediment on the top of that internal part of the crater, Mount Sharp, that is above the crater. So somehow it's sedimented up above the crater. That's very bizarre, right? And I think the thing that I like to think about when I think about that picture and setting up my lawn chair is that if there was a groundwater table at all, and it's not more than, let's say, 100 meters below the surface of Mars, the lake has to be that deep. It has to be. And so there is a central, like from the impact, there is a central mountain that was formed and then got sedimented the pond. So I think that there is plausibility that there is a lake that has a mountain in the middle of it. And then we don't really, in that picture, we don't really know what's going on under the lake surface. It could be all empty. But yeah, all of those things, I like to look at that picture and just think about it, to be totally honest. I don't think it's particularly realistic.
Great. Let's go to another question online. And this person asks, is Curiosity the best electric car ever? How does it work and how much longer will it be working?
Yes, it's the best everything ever. Curiosity is amazing. So Curiosity again has a nuclear generator on it that is generating heat. Of course, as the radioisotopes decay, the power output decays from the RTG as well. And so right now we're on extended mission or EM4. And those are, I think, about 3 years apiece. So we're on extended mission 4. We're positive there's going to be an extended mission 5. So that's another 3 more years after that, unless something catastrophic happens. So we are confident that with the state of the RTG in the battery today, that we can go for 5, 6 more years. After that, things start to drop off pretty quickly, sadly, and probably won't be able to do any analyses.
Clearly, Curiosity is the best of the rovers, but what
It is.
is Perseverance doing differently?
So Perseverance's main goal is sample return, right? So Perseverance on it has a chem. It's called SuperCam because they had a rebrand, but it's the same thing. It has the ability to analyze chemistry. It has something that's called Pixel, which is a lot like the APXS on Curiosity. Again, X-ray or alpha particle X-ray spectroscopy. So you can do chemistry. The really cool thing that Perseverance can do with Pixel is lay that down and then have basically a map of the chemistry of the surface material. It doesn't have the X-ray diffractometer, does not have the mass spectrometers. They took all of that out to be able to store samples inside of the rover. And so its, again, main goal, main mission is to return samples to Earth within a decade from now. And in the meantime, they put some chemistry, some ability to analyze habitability on it, but it's not quite as good. Yeah.
Great. Is it assumed that there just wasn't enough time for life to have evolved? Are we just still hoping for evidence anyway?
Yeah, I think my favorite thing that I've read over the last several years was in a paper that stated that even months seems like too long to originate life, right? So once it goes, right? So you don't need time, really. You just need the ingredients in the process to happen.
Great. Any other questions here in person at the library? Just raise your hand. So the question is, what is the temperature of the laser when it hits the rock?
Yeah, it turns it into a plasma. So like sun hot. I don't actually know the type of laser, but I can tell you it was originally developed to analyze things in places where you can't go. For example, it was developed at Los Alamos National Laboratory is where it was developed. So for, I think, nuclear weapon security was the original reason it was developed. And yeah, it's funny because, like, can you imagine that thing roving around the planet and just zapping lasers around? Like, they make libs here, but they're covered and you have to sort of put them down. It has to be completely dark before you can use it. But there's a lot of blind Martians out there if they're there because we're just zapping everything with this laser all the time. Yeah, so it vaporizes it, and then and it's pretty, like, so on SuperCam, the one that's on Perseverance, they've actually listened to it hitting the rock. They have microphones on SuperCam. You can hear it. And so we usually do 20 spots or so on a single analysis and then average those to get the full analysis. One of the coolest things about that is as you're zapping it, the dust is flying off. So you actually get to remove that veneer of stuff that has nothing to do with the rock underneath it. And then you only really pay attention to the later analysis.
Awesome. going to another online question. How does the different type of salt produced on Mars impact the potential life that might have been able to develop there?
Yeah, it's a great question. So this magnesium sulfate stuff, as I mentioned, tells us or shows us that there's very little water left, essentially, that you're so salty that you have very little water actually in solution. And so there's the concept of the activity of water. So how can water actually participate in chemical and biological reactions? And on Earth, we all sort of have the idea of, if the activity of water is too low, so the food industry actually does this, if the activity of water is too low, then you're totally fine. It's never gonna spoil your food. And so that's one example of that is soy sauce, right? The activity of water in soy sauce is so low that there's actually nothing gonna grow in there. You can just leave it on the counter and it's not gonna get mold or anything. And so that specific thing about magnesium sulfates means that the water activity drops in the solution, and therefore it's much harder for life to thrive in those conditions. And so the types of organisms that live in magnesium sulfate lakes on Earth had to adapt to those, and they adapted to those by making different body structures, having much lower surface area to volume ratio, and so on. The question is whether a primordial organism that's not very good at this yet could possibly have ever started such a situation.
Does the rover talk directly to Earth, or does it have to go through one of the relay satellites around in orbit?
Yeah, it does talk to one of those satellites and it comes back from them. So there was recently one of them, I'm not remembering which one, was taking a ton of pictures for its 10th anniversary, and therefore we couldn't send any commands to the rover or get any new data from the rover for a few days, and that was a huge pain in the butt. But yeah, and it goes through the deep space network, so receiving satellites in places like Australia and so on that then relay the data to us.
Another question from online. Was any drilling into the lake sediment carried out before it began the ascent of Mount Sharp?
Yeah, so the first thing it did actually was scoop up some dust. And so that dust was actually really quite interesting. It was called rock nest. And then they, in the pathway, they actually had to go, because you don't want to land on the steep cliff of the mountain. You kind of want to land in the flattest, most boring place of the crater. And so it landed quite far away from the mountain. So it drilled sequentially a handful of spots as it crossed the flat part of the bottom of the crater before it started climbing the mountain. And that's sort of where we get this, within a month or a year of the beginning of the mission, we already achieved success. We already showed a habitable environment on Mars.
Great, thank you. How long do you think it took to make enough hydrogen to significantly warm the early Martian atmosphere?
How long do I think it took? So the concept is, or at least the calculations that we've done, is that it would, in principle, only take on the order of thousands of years to actually overcome that escape rate and produce enough hydrogen to actually accumulate over what you need in order to turn the faucet on so that the bucket is filling faster than it's emptying, basically, and you're escaping, or you're making hydrogen faster than it's escaping. So that could take, on the order of thousands of years. But the problem is then you sort of run out of fresh rock to react. And so you might then turn it off simply because you've run out of rock to react with.
Hello. But seriously, where are you hiding the aliens? No, I'm just kidding. No, my question is just sort of, I really loved your enthusiasm. You can see the passion for this. And I was just curious for you, if you could go on a human crewed mission there, where would you want to go on Mars and what would you want to do?
Yeah, that's a good question. I think I could happily even land in Gale or Jezero. These places, I think Jezero is very interesting because Jezero has a ton of olivine in it, right? So it's sort of, there's lots of probably serpentinization and other reactions that happen there. I think me personally, I think that we always are going to suffer from having these materials that are just altered by UV fluxes over 3.5 billion years, right? Basically the surface of the planet is what was there 3.5 billion years ago. And so colleague of mine at the University of Calgary and I have been thinking a lot about, well, what if we devise a way to drill deeper into the planet and actually get samples from a place that's not affected by this massive solar flux? Would we end up with very interesting and useful results that have, a lot to say in terms of ancient habitability, but then also the primary mineralogy before it just got bombarded by UV photons for so long. And then also you get to see what the original organic materials look like, and they have been degraded as well. Yeah. So I would drill in the subsurface. Yeah.
Great, thank you. It looks like those are all the questions from online. And if there's any questions here in person, just raise your hand. If not, I'm sure. Oh, we have a question right there. So the question was,
in the space of possible outcome.
Yeah.
the question was, is there a probability of terraforming Mars?
I recently read The Martian. I can say yes based on that book alone. But no, more seriously, so one of the instruments that's on Perseverance is called MOXIE, and so they've now demonstrated that you can make oxygen from CO2 on Mars, essentially. And so that is interesting. You're getting closer to being in a place that people could actually live on the planet. The problem, as I just mentioned, is that there is just UV photons hammering the planet at all time. And so even if you do get there, probably not going to be able to stay very long unless you stay inside all the time or something better. You have very high performance materials that actually enable you to live there.
Great. That looks like that's all the questions. Again, we'd like to thank you very much for joining us here this evening. That was an amazing lecture.